Next, let's talk about a special type of binary tree, which is called a binary search tree, or BST for short. Binary search trees are pretty much exactly like binary trees, except they have a certain sorted property to them. They're not literally sorted like an array would be, but they have a sorted property which actually allows us to use them similar to how we used a sorted array, especially when we were doing that binary search algorithm, which is sort of why these are called binary search trees. So what is that sorted property? Well, it's very simple. For every single node in the tree, the guarantee of BSTs is that every single node in the left subtree, we call this a subtree. This entire thing is the BST, but this is a subtree. Everything in the left subtree has to be less than the root value, and every single node in the right subtree has to be greater than the root value. Now, what about the case where there's equal values? What if instead of this being a 3, it was actually a 2? Well, generally speaking, binary search trees do not contain duplicates, so we don't have to worry about that case. So when we're talking about the left subtree having values that are strictly less than 2, and we're talking about values in the right subtree having values that are strictly greater than 2. But what about this tree? Is this a binary search tree? Well, every value in the right subtree is greater. 3 is greater than 2. What about the left subtree? 1 is less than 2. 4 is not less than 2. 4 is in the wrong spot. Can you tell me where the 4 should actually go? Well, first of all, it has to go in the right subtree. Okay, but where should we insert it now? Now we're at the 3 node. I mean, I guess the 4 could either go here or it could go here. Let's put it over here. Does this satisfy the requirement of a binary search tree? Well, 4 is greater than 2 and it's in the right subtree. Should that be enough? No, it's not, because the definition of a binary search tree is actually recursive, which means that the sorted property is not only true for the root node, it's true for every single node in the tree. In other words, it applies not only to the tree, but also to every single subtree as well. So we call that recursive because from the perspective of this node, this is its own tree. We call it a subtree because we know it does have a parent, but this is essentially the exact same as any other binary search tree. It should have the same properties. It has to be sorted. So when we look at this node, we check, are all the values in the right subtree greater than 3? Well, it doesn't have any right children. What about the left subtree? Are all values here less than 3? It's not true. 4 is not less than 3. So we can't put the 4 over here. We have to put it over here. Now you might be wondering why. Why do we care about having a sorted property with this data structure? What does it achieve for us? Well, pretty much exactly the same thing as having a sorted array. With a sorted array, when we need to search for a value, we can do it in log n time. If the array was not sorted, we would have to look at every individual element, so we would have to search for a value that we're looking for in O of n time. But with sorting, we can do it more efficiently. The exact same thing is true for binary search trees. If it didn't have a sorted property, we would have to look at every single node to find some target value. But with the sorted property, we don't. We can follow the same logic as binary search. Suppose we're looking for a target value of 5 in this case. We start at the root. We're looking for 5. Is this 5? No, it's 2. Okay, so we didn't find the target. But is our target greater than 2 or is it less than 2? Well, it's 5, so it's greater than 2. So this wasn't the target, but now tell me, which direction are we going to look? Are we going to go left or are we going to go right? Well, we know with binary search trees, all values greater than 2 are going to be on the right side. So if 5 exists, it must be somewhere over here. So by making that comparison, we not only eliminated this value, but we also eliminated everything in the left subtree. In this case, it's only one value, but it could have been a bunch of nodes. And by doing a single comparison, we eliminated roughly half of the possibilities. And then we would continue. Now we would look at the right child here, and we would do the same exact comparison. This is not equal to 5, but is 5 greater than 3 or less than 3? It's greater than 3, so we're going to go look to the right. We would have eliminated anything on the left, but there isn't anything here anyway. So now we're at pretty much the last node. Is this equal to 5? It's not. 5 is greater than 4, so we're going to go down to the right. But at this point, we reach null. There's no more nodes left that are greater than 4. So basically, we did not find the target that we were looking for. So let's say we were returning true or false, whether we find the target. In this case, we didn't find the target, so maybe we would return false. If we do find the target, we could return true. So that's the idea, and it's pretty simple when you're looking at a picture for how to perform this search algorithm. Now let's take a look at the code. Since binary trees are recursive in nature, meaning a subtree has the exact same structure as the entire tree, we can expect to use a recursive algorithm to traverse it and to search for values in it. Now, it's not required to use recursion, actually. There are other ways to do this, but the easiest way by far is recursion once you can get familiar with it, which is why we talked about recursion earlier in the course. Now, even though this data structure has two branches, right? It has left and right children. To search along a binary tree is actually one branch recursion. The reason is when we get to a node, we do our comparison based on whatever the target value happens to be, and we only go in one direction. We're going to recursively either go along the left subtree or the right subtree. There's no need to do both with binary search trees. That's the efficient part. Let's suppose our target was 3 in this case. You can see the search function is going to take the root of some binary tree and some target value. We're going to search for that target value. And let's start with the base case, which is the simplest one, but it's the one that we're going to reach lastly, of course. We saw in the previous example where we were searching for a 5, we started here, then we got here, and then we got here, and then we went to the right child of this node, but that's when we reached the null case. So in general, if the root node is equal to null, we're going to return false because that means we ran out of nodes to search and we didn't find the target, so we can return false. But if that's not the case, that means we have a valid node. Let's assume we started at the root. We're at this node currently. We're going to do a few comparisons that might look very similar to the binary search comparisons we were doing earlier. We're going to check, is our target greater than the root value, or is it less than the root value? Or if it's not greater and it's not less, that must mean it's equal, so we can return true. So in this case, our target is 3, which is greater than 2. So what we're going to do is recursively call search. But where are we going to do it? Are we going to go to the left node or the right node? Or are we going to stay at the root? No, we're going to go to the right node. So we're going to pass in as the node root.right. We're going to run search on this child node. So this is the recursion part. This is the sub problem that we're going to run search on. First, we started with the whole tree. Now we know it's not that, but this is the sub problem now. So now, being at this node, we know that this is not a null node. We're still looking for 3. Is our target greater than 3? Nope. Is it less than 3? Nope. It's exactly equal. So at this point, we return true. But when we return true, this return call is going to go back up to the parent because remember, we're inside of a recursive call. So where did the parent call search on the child? Well, we remember it was this conditional where we called search on this node. Now we're going to return whatever the result of that was, whether it was true or false. In this case, it was true, so we're going to end up returning true from here, which means we're returning true from here. That means this entire tree does contain this target value. So what's the time complexity of performing this search? Well, just like binary search, it's going to be log n. That's the benefit. But the asterisk with that is that it's only going to be log n if we have a binary tree that's roughly balanced, because our assumption is when we get to a node and we choose either to go left or go right, as we do that, we're eliminating half of the possibilities every single time, half of the remaining possibilities. So from here, we would eliminate half of the possibilities and continue doing that. But we can only do that if the tree is roughly balanced. When we say balanced, that means for every single subtree, including the root tree, the heights of the left and right subtrees are roughly equal, meaning that they differ by maybe 1. That would be a perfectly balanced tree. In this case, this tree is balanced because the height of the left subtree here is 1, the height of the right subtree is 2, so they differ by only 1. What about the left and right subtree of this node? Well, it's 0 here and 0 here, so they differ by 0. What about this node? The height of the left subtree is 0, the height of the right subtree is 1, so the difference is 1. And lastly, for this leaf node, again, the heights of the left and right subtrees are 0, so the difference is 0. So this is a balanced tree. But we might not have a balanced tree. What if we didn't have this node and we just had a big string of nodes going like this? Well, this is essentially a linked list, and we could have values like 5 and 6. While this is sorted, the way our binary search is going to run, we can't just go halfway in between all of these nodes. We're going to start here, say, okay, our target is too big, go here, maybe our target is too big again, and it could just keep going like that. And in this case, clearly, we're not eliminating half of the possibilities every single time. So if the tree is like this, where it's not balanced, the search algorithm in the worst case would be big O of n. But the reason we have binary search trees is to have balanced binary search trees. And it's usually assumed that if you're working with one, you do have a balanced tree, which would usually be log n. But in terms of technicalities, a lot of people will say the time complexity of running search is going to be big O of h, where h is the height of the tree, which makes sense. Because for an imbalanced BST, the height would be n, because we just have a string of nodes like this. But for a balanced tree, the height would be log n for similar reasons we talked about earlier in the course, especially when it comes to merge sort, right? We know this is being multiplied by 2 every single time. So then the height of that would be log n. So this was definitely a lot to take in, but there's one last question I want to answer for you, and that is, why do we have binary search trees if we can already have sorted arrays? If we already have sorted arrays which we can run binary search on, we can already search for values in log n time. So why create all this complexity to create a complicated data structure just to achieve the exact same thing? Well, the downside of having sorted arrays is if you want to add values to the array and remove values from the array and keep the sorted property of that, well, we know removing from an array in the worst case is going to be big O of n, because even if we can find the value really quickly, we still have to then maybe shift over every single value in the array. And if we want to add a value, like if we wanted to add a value over here, then we would have to take all of these and then shift them over by 1. So when it comes to inserting and deleting from an array, it's always going to be big O of n, whether it's sorted or not. But that's not true for binary search trees. With binary search trees, inserting values and deleting values can also be log n. That's what we're going to talk about next. And that's the main benefit of binary search trees.